In this video, we're going to talk a bit about how we establish a resting membrane potential in a neuron. This is the basis behind how a neuron works, is that a neuron at the membrane establishes a different electrical gradient or potential from the outside side of the membrane to the inside. And this is going to be the basis of how we get an action potential to create and fire and move itself along a neuron's membrane. So let's start to have a look at some of the factors that establish this resting membrane potential. So what types of things do we have to work with that can establish, a positive and negative region? And overall, what the goal is to have a more positive region on the outside and a more negative region on the inside. Now, this is in comparison to each other. And I also want to point out we're really talking about an area really close to the neuron cell membrane. We're really looking at just outside and just inside, where we're comparing the difference between positive and negative. So the things that we can work with would be basically potassium, and of course potassium has a positive charge, sodium, which also has a positive charge. There's other things like chloride and other ions that also come into play, but we're really going to focus in on the sodium, potassium. The other ones do contribute something, but we're going to keep our discussion focused on here. And then we also have, and I'm just going to shorthand it here, pro for proteins. Okay, we do have proteins and other organic molecules, and many of them have an overall negative charge. So we have these organic molecules such as proteins and other things that will contribute a negative charge. So let's start with the organic molecules. I'm going to change the color for them. Let's make them blue. So I'm going to make squiggly lines. Squiggly lines are organic molecules. These are large organic molecules that are inside the neuron. And remember, overall, many of them have a negative charge. I'll just draw a little negative to remind us. And that contributes to some of the negativity inside the cell membrane. Now let's look at potassium, and let's make potassium, we'll go for orange for potassium. So let's look at potassium. It's positive. Now, what we're going to see once I set up the concentration gradient, I'm predominantly going to have more potassium inside the cell than outside, and more sodium on the outside versus inside. Now let's just look at potassium and what potassium is doing. So potassium is inside the cell, but there are these little channels, little potassium channels, and these are open all the time. And potassium has the ability to leave the cell, and it has the ability to enter the cell. Now, what types of things are driving potassium to either leave or enter? Well, think about it. If I have a lot of potassium inside the cell, all right, let's draw a lot of potassiums inside the cell, and there's very few potassium on the outside, of course, there'll be this force that will try and drive some of the potassium out. And you can think of some of the forces that would do that. First of all, I'm going from a high concentration of potassium to a lower concentration. So that would be a force that would drive some potassium out. The other thing is, if I have all these positive ions, they want to repel each other. So that also will force potassium out. So not all the potassium will leave, but certainly some of the potassium will be driven outside the cell, or the neuron to be more specific. Now, that potassium, some of it will stay out there, but a lot of potassium, once it's out here, will basically be drawn back in. Now, why is it going to be drawn back in? Is part of it is because potassium is positive and there's a lot of negative. There's a lot of negative organic molecules here. So there'll be sort of that pull of a positive being pulled towards a negative, and that will help to draw it back in. And these are just some of the sources, some of the forces, I should say, that are causing potassium. So potassium, some will leak out, and then re-enter the cell. So there's almost like this little trickle of some of the potassium, not all, out, and it trickles back in. And eventually you do hit a point when you're establishing a resting membrane potential that the movement of potassium out is equal to the movement of potassium in. So it hits a steady state. So potassium can come and go, but overall, more potassium will be inside the cell versus outside the cell. Now let's have a look at sodium. Just change the color for sodium. There are also sodium gates, or channels, I should say. And sodium is much more concentrated on the outside versus the inside. Now, sodium has a harder time to leak in and leak out, but it may. So there is a little bit of leakage of sodium in to go from high concentration to low concentration. And then we can have a little bit of leakage out, but that's a very small amount. It's really the potassium that moves quite easily. So now what we have to do is we have to then look at another aspect. And the next aspect is the sodium-potassium pump. Because I've set up this model where I have a huge influence by these large organic molecules, which are contributing to the negative. I have a whole bunch of potassium that's in here. There's more potassium in the intercellular fluid versus the extra. And to give you an idea, it's about 40 times greater concentration of potassium inside and out. Now, there's also the sodium-potassium pump. And we'll put the sodium-potassium pump now on here. And the sodium-potassium pump we've already talked about. And remember, it's a pump, and it requires the use of ATP. And the role of the sodium-potassium pump is to basically pump out 3 sodiums. So for every time the pump fires, I have 3 sodiums that move out, and correspondingly, I have 2 potassiums that move in. So every time the pump runs, I get a net gain of 1 positive. And it's just, of course, it's just a simple math, is that if I'm pumping 3 positive out and 2 positive in, well, the net gain is every time I burn up an ATP and fire the pump, I get a net gain of 1 positive on the outside. So the sodium-potassium pump has a role in helping to maintain and fine-tune the voltage difference between outside the cell and inside the cell. Now, to give you an idea that sodium's concentration, sodium is about 12 times more concentrated outside versus inside. Now, I also want to point out, these pumps are running really continuously. And because we're burning up ATP, this is really a huge energy demand for the nervous system. And somewhere about 70% of the energy used by the nervous system is to run these sodium-potassium pumps. And this has to go on a regular basis because a neuron is just sitting there waiting to find out if it's going to fire or not fire. And if it is going to fire, it has to have set up this situation where it has a positive on the outside and negative charge on the inside. Because, as we'll see when we talk about action potentials, an action potential is basically where we're going to open gates and sodium will flow in large amounts, making the inside more positive, and then potentially potassium will flow out to counterbalance that, and that will be part of the action potential. So in very quick review, when we're looking at establishing a basically resting membrane potential, we're looking at a few factors. One is that we have these large organic molecules. Now, I didn't mention it, but you could probably imagine that these large organic molecules they cannot cross the membrane. So they don't move back and forth. They stay where they are. So, and they make up this big pool of sort of negativity within the cell, just underneath the cell membrane. The potassium itself is quite movable. We have much more potassium inside versus outside once we establish the gradient. But remember, potassium can sneak out and can sneak back in, and eventually hits a point that the amount going out is equal to the amount going in. Sodium can move through a little bit, but it's nowhere near potassium. And the sodium-potassium pumps, which use ATP, help to basically fine-tune the difference between the positive on the outside and the negative to get us that resting membrane potential. By burning up ATP, I transport 3 sodium out and 2 potassium in. And once that's done, I've now established the resting membrane potential. Now, because of the leakage of some of the ions, the pump has to keep going. It's like a bit of a leaky boat that you're always slightly bailing the water out of the boat as you're going along because a little bit of water's leaking in. Same thing is that I have to run the sodium-potassium pumps continuously to maintain the positive versus negative balance. And that's the basis of the resting membrane potential.